Good evening to all. Yesterday in the end session we discussed Laplace transform with properties along with note point gamma of proper fraction, positive fraction, negative fraction, positive integer. Okay, so once again I am giving an example for gamma of a negative fraction. After that we will start a basic problems on these standard functions using linearity property, then problems on inverse using partial fractions, and then properties followed by unit step function, next to ordinary differential equation, some problems which are not solved by original CFPA method, that problem solved by Laplace transform. So these are the topics in the today's class. Okay, so I hope that you are all prepared that what we discussed yesterday, that properties, not properties, basic Laplace transforms, inverse Laplace transforms along with the note point. Gamma 1 I have given 1, gamma half root pi, positive integer I have given, negative integer so what is that fourth point? If n is a negative fraction comma define gamma n is equal to gamma n plus 1 divided by n. So for negative fractions apply this gamma procedure. Okay, evaluation of a negative fraction gamma. Example, gamma minus 5 by 2. So this is your n is equal to minus 5 by 2. Using that, n plus 1 becomes minus 3 by 2 divided by n, that is minus 5 by 2. So still minus 3 by 2 is negative fraction. Apply the procedure until to reach a proper fraction. Okay, so this is inverted, the denominator fraction comes into the numerator reverted. So gamma minus 3 by 2, using that gamma minus half divided by n means minus 3 by 2. So this is minus 2 by 5 minus 2 by 3. Still minus half is a negative fraction. Apply the above formula. N plus 1 becomes plus half divided by n. So this is finally simplifies to minus 2 by 5 minus 2 by 3 minus 2 by 1 into the gamma half is root pi. Gamma function is not defined for 0 or a negative integer. So gamma function is defined for positive integer, positive fraction, negative fraction, but not for 0 or negative integer. Gamma 0 tends to plus infinity, gamma minus 1 tends to minus infinity, gamma minus 2 tends to plus infinity. Alternatively it is going to like that. Next, linearity properties in Laplace and inverse is, that is Laplace of sum or difference of t terms can be written as sum or difference of their Laplace transform. That is, Laplace is applicable for individual terms, individual t terms, whenever it is in the form of sum of two terms, two t terms, or difference of three terms, like that. Similarly inverse also. Okay, that is called linearity property. Now I am giving you, now we discuss Laplace transform problems using that standard formulas given by me yesterday. Okay, similarly inverse, one by one. Find the Laplace transform. LT stands for Laplace transform of the following. First one, a plus bt whole square, this is given 1999. 2 sine square 2t, this is given 2000. 3, yesterday I have given in the doubts and sessions some trigonometric relations, transformations, trigonometric multiple and submultiple angles, that formulas you should remember. Okay, root t minus 1 by 1 over root t whole square, or you can set with root whole cube. 4 2 e power minus t minus 3 cos h 2t. So these are the 4 problems I have considered. Five sine cube t. Just see here, one by one solutions. First one, L of a plus bt whole square, a comma b are constants. So expanding using that a plus b whole square, which gives a square plus 2abt plus b square t square. So here sum of 3 terms, Laplace can be expressed as sum of their Laplaces, that is L is applicable to each of the terms whenever it is in sum or difference of the given terms. Okay, so this is L of a square constant, a square over s, 2ab constant, bring outside, L of t, that is t raised to n is equal to 0 1 2 3, that I have given n factorial by s raised to n plus 1. So 1 factorial divided by s square plus b square t square, n is equal to 2 factorial by s cube. Factorial by s cube. Later you simplify further depending on the options. 2 L of sine square 2t, which is in the form of 2 sine square a, there is no 2, so first multiply by 2 and divide by 2, keeping that half outside and comparing now with this 2 sine square a formula is 1 minus cos 2a. So 1 minus cos 2 into a, that becomes 4t. So L of 1 is 1 over s minus L of cos at, a is equal to 4, s over s square plus a square means 16, and taking LCM and further simplification depending on the options only. Okay, next 3 L of root over t minus 1 over root over t whole cube is equal to, it is in the form of a minus b whole cube, a cube minus 3a square b plus 3ab square minus b cube. So this simplifies to root t whole cube minus 3 root t whole square into 1 over root t plus 3 root t into 1 over root t whole square minus 1 over root t whole cube. So Laplace is now applicable for each of the terms. Okay, so this is equal to L of t raised to 3 over 2 minus 3 times L of t power 1 by 2 plus 3 times L of t power minus 1 over 2 minus L of t power minus 3 by 2. So each is in the form of last Laplace of t raised to n. N is a fraction, but not for a negative integer. Okay. So this is equal to gamma 5 by 2 divided by s over s divided by s power 5 by 2. That is gamma n plus 1 by s power n plus 1. Okay. Minus 3 times gamma n plus 1, half plus 1 becomes 3 by 2 divided by s power 3 by 2 plus 3 times n is equal minus half, n plus 1 becomes half, that is gamma half divided by s power half, and the last one n is equal to minus 3 by 2. After adding 1 it becomes gamma minus 1 by 2 divided by s power minus 1 by 2. And you know how to evaluate gamma of a positive fraction, negative fraction, I shown you. So gamma 5 by 2 is 3 by 2, 1 by 2, root over pi, s power 5 by 2. The first fraction simplification. Minus 3 times gamma 3 by 2 is half into root pi divided by s power 3 by 2. Okay. So just I am continuing here, plus 3 times gamma half is nothing but root pi divided by s power 1 by 2, and the last one minus gamma half minus half is minus 2 by 1 into root over pi divided by s power minus half, and later you simplify depending on the options. Just I have done gamma of negative fraction and positive fraction, the last two terms, and the other two terms I have written in this step. Fourth one. L of 2 times e power minus t minus 3 cos h2t is equal to e power at a is equal to minus 1 or e power minus at a is equal to 1, cos h at a is equal to 2. So 2 times 1 over s plus 1 minus 3 times cos h at s over s square plus s square minus a square, that is minus 4. And the fifth one is L of sin cube t. It is in the form of sin cube a, that is L of 1 by 4 times 3 sin a minus sin 3a. Just I applied sin 3a, along with from that I have expressed sin cube a formula. So keep the constant outside and the Laplace for other terms. L of sin t, a is equal to 1 over s square plus a square, minus the other constant is for second term is 1 over 4, L of sin 3t, a is equal to 3 over s square plus 9. This is the answer. continue the above problems. One more problem which is given 1999. Find the Laplace transform of f of t is equal to k if 0 less than t less than c is equal to 0 t greater than c. So this is function defined in two different subintervals, that is 0 to c and c to infinity. Anyhow, the Laplace is defined for 0 to infinity, unilateral Laplace transform, and it is called piecewise continuous function also. Okay. Solution. So these problems whose Laplace are obtained by using definition of Laplace transform, that is 0 to infinity. By definition, L of f of t is equal to integral 0 to infinity exponential minus st into f of t dt. Okay. Now this 0 to infinity, using definite integral properties, I can write 0 to c whose function value is given k, plus c to infinity that tells that t greater than c whose function value is 0. So this second part is 0. The first part, k is constant, take outside. E power ax integration is e power ax divided by a, where a is equal to minus s, x variable is now t variable. So 0 to infinity. So this is simplifies to, first of all, this 0 1 minus 1, that is k over s. 0 to c, upper limit is c in the first case. So this simplifies to 1 over s 1 minus e power minus cs, not 1 over s, k over s. The same problems we can find the Laplace with the help of unit step function, which we are going to discuss later. Just without unit step function, how we evaluated, that is purely on integration. Okay. So sometimes integration by parts takes lot time. Okay. In such cases, to avoid that problems, we will evaluate such problems, Laplace problems, with the help of unit step function, that we are going to discuss later. Here no complicated integration, simple integration only. Sometimes for time purpose, that means for saving time, number of steps, avoiding integrations, we can do that problems with the help of unit step functions. Okay. Next, some problems in inverse. Find the inverse LT, Laplace transform of, first one, 3 into s square minus 2 whole square by 2s power 5. Second one, 2s minus 8 divided by 3s square plus 9. 3. 1 over s cos 1 over s. Solution. First one, using standard formulas and simplifications, algebraic formulas, trigonometric formulas, if any applicable, apply. Okay. Three times s square minus 2 whole square by 2s power 5. First, the common constant, whenever a constant is multiplying, keep outside. That is tells that linearity. So 3 over 2 times L inverse expanding a minus b whole square, that s power 4 minus 4s square plus 4 divided by s power 5. Splitting into fractions, this is 3 by 2 L inverse 1 over s minus 4 times 1 over s cube plus 4 times 1 over s power 5. Except that constant remaining all are in the form of 1 over s power n plus 1, that is t power n by n factorial, because n is equal to 0, 1, 2, 3, and 1 over s I have given, that is 1 inverse. So using linearity property, this is 3 by 2 times 1 minus 4 times t square by 2 factorial plus 4 times t power 4 by 4 factorial. Later you simplify depending on the options. Second one, L inverse 2s minus 8 over 3s square plus 4. Sorry, 3s square plus 9. Now the denominator is in the form of s square plus a square after taking 3 out. Okay, and so numerator 2 terms. I didn't give directly 2s minus s minus something, any inverse formulas. So splitting into fractions, and before that take the common constants outside. So here first term 2 divided by 3. 2 is common, 3 is also common, and then L inverse s over s square plus 3 can be written as root 3 whole square, because I want to compare the standard formulas. Okay, and minus 8 by 3 into L inverse 1 over s square plus root 3 whole square. Due to this only I have considered in inverse formulas yesterday 1 over s square plus a square instead of a over s square plus a square. Okay, so this is 2 over 3 times cos at root 3 t minus 8 by 3 into sin at root 3 t divided by a, using standard formulas. 3. L inverse 1 over s cos 1 over s. So cos 1 by s I didn't give direct formula in inverse formula. So just compare with the Taylor series cos x, what we have learnt in Max 1 paper calculus. Okay. So cos x, just compare with x here 1 over s. So this is L inverse 1 over s times, what is cos x expansion, Maclaurin series expansion, 1 minus x square over 2 factorial plus x power 4 by 4 factorial, etc., where x is equal here 1 over s. 1 minus 1 minus x square over 2 factorial plus x power 4 by 4 factorial, etc. Where x is equal here 1 over s. 1 minus that is the procedure. Okay. Now multiply that 1 by s to inside terms and separate. L inverse. First term is 1 by s minus 1 by 2 factorial 1 over s cube plus 1 over 4 factorial into 1 over s power 5 minus so on. So 1 over s is 1 minus 1 over s cube is t square by 2 factorial. Already there is 2 factorial. So this becomes whole square plus this becomes t power 4 by 4 factorial whole square using the last standard formula in inverse. Similarly, other type just using partial fraction, but the method is not mentioned. We only identify which is applicable. Again, find the inverse Laplace transform of first one is 2s square minus 6s plus 5 divided by s cube minus 6s square plus 11s minus 6. 2. This is 1996. S plus 5 divided by s plus 1 times s plus 3. 1 over s square 2s square plus 3s plus 1 1 over s square into s plus 1 So this is 2010, this is 2009, fifth one, s square plus 1, s square plus 4 times s square plus 9. See, first of all, there are partial fractions are valid if the numerator degree less than denominator degree, that is proper fractions. Now there are two types of factors in the denominator: linear factor, that is power 1 factor, and other factor is quadratic factor, that is second degree term. So in this there are four types: linear factors which are non-repeated. So for example, that is, see that second problem, both are non-repeated, both are distinct. In such cases the partial fraction is a by s, so a by first fraction plus c by or plus b by second fraction, that is second denominator, second factor. Suppose if a linear factor is repeated, so go to that fourth problem, s square. S square can be written as s times s, that is s into s. So s is repeated 2 times. In such cases the partial fraction is first a over s plus b over s square. Similarly, if it is s cube, c over s cube, etc. Next, if any quadratic factor, say s square plus 1, look at that fifth problem in the denominator, s square plus 4, which is not factorizable to linear factors. In such cases the partial fraction is as plus b. If any next factor, cs plus d. Similarly, non-repeated, repeated, what we have discussed in the linear case. Okay. So in all these the numerator degree less than denominator degree, so all are valid before applying the partial fractions. So I am going to do different type of problems. If a problem is repeated with any procedure, then you only do it. I will give the hint. So in the first problem, the denominator is cubic factor. If possible, find the factors. If you do not get any factor, then it is difficult to evaluate by partial fractions. Okay, and any other method also. So see, the factors are getting all the three linear factors. First one, 2s square minus 6s plus 5 divided by s cube minus 6s square plus 11s minus 6. So what are the three factors here? Using equate denominator 0, then s is equal to 1, first value of s is equal to 1 satisfies the equation. That we have shown you one problem in auxiliary equation, differential equations. Other roots are obtained by Horner's method or synthetic division. Okay. So the three factors for the denominator is 2s square minus 6s plus 5 divided by s minus 1 times s minus 2, s minus 3. All the three are linear factors which are non-repeated. So the corresponding partial fraction is a over s minus 1, b over s minus 2, c over s minus 3. So this can be written as a over s minus 1 plus b over s minus 2 plus c over s minus 3. Okay, now what we have adopted the procedure in 11th standard or 12th standard, the partial fractions taking LCM and then comparing coefficients or putting s is equal to 1, 2, 3 which are obtained from the respective denominators. Okay, so then you will be getting respectively ABC values. So that procedure is called direct method. Now what is indirect method? That means same what I am doing without taking LCM and cancelling. So just observe the procedure. So what is the first fraction? That is s minus 1. Now we have to determine a. Okay, to get a, what is the corresponding s value? That is in the denominator after equate to 0, s is equal to 1. Put that s is equal to 1 in the left side. This is your left side, this is your right side. In the right side, we have to find ABC values respectively. Okay. So what is the corresponding denominator? S value in the first fraction, s is equal to 1. Put that value in the left side, closing the corresponding factor. Otherwise, every denominator becomes 0. So in all the other values of s of the left side, put s is equal to 1. 2 plus 5, 7 minus 6, 1. 1 minus 2 minus 1. 1 minus 3 minus 2. So finally, it simplifies to 1 over 2. Or if you do not understand this one, then you do, that is, it will take only one or just takes the just difference is 1 or 2 steps only, and the time is also 3 to 5 seconds only. Okay, if you are habituated that your direct method, what we have adopted, that what we have learned in 11th standard, that is also here applicable. Next, to get b, what is the corresponding denominator? That s value, s is equal to 2. Put s is equal to 2, closing this factor in all the remaining. This is 8 plus 5, 13 minus 12, 1. This is 2 minus 1, 1. 2 minus 3, minus 1. This finally simplifies to minus 1. To get c, the corresponding denominator s minus 3, that is the value of s is 3. That is, put s is equal to 3 in the left side except in that factor. So 2 into 3 is equal to 18 minus 18 cancel, 5 by 3 minus 1, 3 minus 2. So this finally simplifies to 5 over 2. C value is 5 by 2. Okay. So therefore, L inverse 2s square minus 6s plus 5 divided by s cube minus 6s square plus 11s minus 6. Okay. Now keep the constant outside. Each is in the form of 1 over s minus a. L inverse 1 over s minus a is e power at. A is equal to 1, 2, 3. So first one is exponential t minus exponential 2t plus 5 over 2 exponential 3t. This is the answer. So this answer is correct or not? If you take LCM on that obtained answer, then simplifies, taking LCM and simplifies to finally this one. You can cross check. So second is a, later you do same non-repeated, and the third also I am giving 1 over 2s square plus 3s plus 1. So here the extremes multiplication 1 into 2, the middle term 3. 3 can be written as 2 plus 1. 2 plus 1 is nothing but 3. 2 into 1 is nothing but 2. So this is a factorizable whose factors are 2s plus 1 into s plus 1. These are the factors. Later you do. Okay. just here 2s plus 1 divided by s plus 1. Now putting s is equal to minus half, closing this factor, 1 minus of half, this simplifies to 2. Putting s is equal to minus 1, this simplifies to minus 1. A value, b value. Later you check. Next, fifth one, let me complete. Fifth problem. So each is of same factor. Highest degree term, s square term is same, and whose coefficient is same, whose symbols are also same. So in such cases, take that common s square term, another variable, a new variable, which becomes into linear factor. S square plus 1 divided by s square plus 4 times s square plus 9. So this can be written as y plus 1 divided by y plus 4 into y plus 9, where y is equal to s square. Where y is equal to s square. Now just this is linear factors case. Okay. So what are the corresponding fractions? Y plus 4 plus y plus 9. So to find a value, put y is equal to minus 4. This simplifies to minus 3 by 5. A value is minus 3 by 5. To get b, put y is equal to minus 9. Minus 9 plus 1 minus 8 by minus 5. 8 over 5. This is b value. And later you simplifies to this is minus 3 by 5 into 1 over y is replaced by original term because it is a known formula, 1 over s square plus 4, and 8 by 5 it is 1 over s square plus 9. So 1 over s square plus a square in the form of sin 80 by a. So therefore L inverse s square plus 1, s square plus 4, s square plus 9 is equal to minus 3 by 5 sin 2t by 2 plus 8 by 5 sin 3t by 3. This is the answer. So there is one problem, fourth problem. Let me complete. Different types of partial fractions over. Fourth problem. L inverse 1 over s square times s plus 1. So here according to the original procedure, a over s plus b over s square plus c over s plus 1, then taking LCM, and then you know the procedure what we have adopted in 11th standard. Okay. Now just see what I am doing. The numerator 1 can be written as s plus 1 minus s square into s plus 1. That means what I have done, adding s and subtracting s, because here just observe, this is s square factor, this is s plus 1. Which factor containing more terms? This is 2 terms, this is 1 term. So in such a case, okay, try to get that same factor in the numerator if possible. Okay, that means that is possible. Just I have added s and subtract s, then splitting into fractions. L inverse 1 over s square minus 1 over s times s plus 1. So again we know 1 over s into s plus 1, that is partial fractions. So that is L inverse 1 over s square is t minus L inverse of 1 over s into s plus 1, partial fractions. So that is 1 over s minus 1 over s plus 1, a by s, b by s plus 1, like that. Okay. Now this simplifies to t minus 1 plus exponential minus t. This is the answer. Next, properties of Laplace transform and simultaneously, if possible, I am giving inverse Laplace transform. Now so far in the last but one step, or in the beginning step, we have evaluated Laplace inverse for using standard functions directly, individual t terms, single terms, okay, or sine, cos, or e power at 1, like that, single terms. Suppose if any multiple terms, sin t by t, that type of problems we cannot evaluate directly using the definition of Laplace transform, using the following properties only. So here the common is, if L of f of t is equal to f bar s, because Laplace of any t term, say f of t, whose answer is in terms of s, that is denoted by f bar s. Yesterday I have given this notation, comma, then first property is first shifting theorem. First shifting theorem. L of e power at into f of t is equal to f bar of s minus a. L of e power minus at into f of t is equal to f bar of s plus a. Let me explain. So, in the given product of t terms, one of the term is e power at or e power minus at. Then you take remaining term as f of t. That means in all these problems, you properly select or identify f of t while comparing that problem with the one by one properties. Suppose we are in the stage of first property. One of the product of the t terms is e power at, e power minus at. In the remaining terms, whatever it may be, immediately you select that f of t. Once you take f of t, then find its Laplace, giving some f bar, some s term answer. Then come to your problem. If it is multiplying by e power at, in this s is replaced by s minus a. If it is multiplying by e power minus at, in this s is replaced by s plus a. Okay? So here inverse also I am giving. Side by side properties. Okay? If L inverse f bar s is equal to f of t, comma, then L inverse f bar of s minus a is equal to, just I am writing in reverse order only, L and L inverse I am changing, into L inverse f bar of s. Similarly, L inverse f bar of s plus a is equal to e power minus at into L inverse f bar of s. See, in inverse problem, how you identify? By first shifting theorem. All s terms in the inside of L inverse operator in the form of s minus a, that is numerator, denominator, everything is in the form of s minus a number a, or all are in the form of s plus a, but not both. In this case, first write e power at, then same L inverse, s minus a is replaced by s, what I explained here, s is replaced by s minus a, here s minus a is replaced by s. So here in this case, e power minus at, s plus a is replaced by s, just reverse order only. Okay. Example. First problem. Find L of e power minus t into 3 sin ht minus 2 cos 3t. Now comparing this problem with this property or this property, e power minus at. So multiplying by the other t term, this is an indicating, this term is indicating taken to be f of t, that is the indication. Okay, solution. So what I underlined, first find Laplace. L of, okay, 3 sin ht minus 2 cos 3t. Basic result, sin hat a is equal to 1, cos at a is equal to 3. So 3 times 1 over s square minus 1 minus 2 times s over s square plus a square, 3 square becomes 9. So this is, I can denote it by f bar s. Why? Because I have selected this term as f of t. Just one second. Therefore, by first shifting theorem, FST, okay, L of e power minus t 3 sin ht minus 2 cos 3t. This is equal to just in this f bar s, e power minus 8 is multiplying, a is equal to 1, s is replaced by s plus 1. 3 times 1 over s plus 1 whole square minus 1 minus 2 times, in this also s is replaced by s plus 1. S plus 1 divided by s plus 1 whole square plus 9. That is the answer.